Today we'll use a few slides, so that we can uh, finish a few topic, faster. It will be, faster to finish, not for all topics, for a few topics, we can use in a PowerPoint, and then we can finish, those topics, faster. We have to finish the four chapters and in time. So let's start with this first topic. Torque on a current in a carrying loop in a uniform magnetic field. We started this topic. Yesterday we calculated the net force, the net magnetic force experienced by this current carrying rectangular loop. The loop is O, A, C, D, O. Has everyone joined or not? Should we start now? Okay. Let's continue. So this rectangular current carrying in a loop, see, one side is A, another side is B. It carries a current I, the current in the loop is I, and it is placed in a region in which you have magnetic field. It is placed in a region in which you have magnetic field. The magnetic field is where the written is stored in a vector form. The magnetic field is where the written is stored. B is in a vector form, and it is written as B. Magnetic field in this region is, I will write it here. In this region is Bxi plus By It is in component form. Bz K. So you have a current carrying loop, and it is placed in a uniform magnetic field. This is the field here. And yesterday, we found out that the net force, magnetic force experienced by this loop is 0. And today we are going to find out the torque, the torque experienced by this loop, current carrying loop in the uniform magnetic field. So first of all, let's find the forces. We can find the forces. Is it the first slide or not? Okay. Okay, let's find the forces here. The force experienced by this arm, OA arm, the magnetic force experienced by OA arm means the wire, OA, it carries current I, its length is an A. So you can use the formula, I for a state wire, you have the formula, for magnetic force, this is I L cross B. Here the length is A. So I'm writing it here as I current in the wire and OA cross B. B is the magnetic field. And C, this is your y-axis. This is your x-axis. This is your x-axis. This is y-axis. And upper one is this one is z-axis. That is perpendicular to the plane of x and y-axis. And Along positive x-axis, you have unity vector I cap. Along a positive y-axis, you have unity vector in j cap, and along positive z-axis, you have unity vector in k cap. So let's calculate the first force. Magnetic force experienced by OA arm is I length and a length of OA arm, length vector cross in a magnetic field. So magnitude of length is A, and its direction, the direction of this length vector is along in a positive and a x-axis. That's why we took the unity vector I cap. And your magnetic field is in a bxi plus byz plus bzk. Now, what will you do? You will simply take a cross product of these two quantities. Means your length vector and your magnetic field. You just take the cross product of the first term will be 0 because you have I in both terms here. I cross I is 0. In cross product, what do you have? AB sine theta. No? A cross B is AB sine theta. And since both the terms have unity vector I, the angle between them is 0 degree. That's why the cross product will be 0. Now you find the cross product of this within this one, and I cross in J is K, and I and A, we put it outside. So you have by k cap. Similarly, you find the cross product of this term with the last one. I cross k is minus j. That's why here you will have IA. We have put outside. So you will have bz and j. I cross k is minus j. That's why we have minus here. Similarly, you find the magnetic force on AC arm. AC arm means length of AC arm, length vector of AC arm, and a magnetic field. And see, your AC vector is your AC vector is parallel to y-axis, and that's why you have a unity vector in the direction of AC vector j cap. See, the direction of AC vector is the same as the direction of your positive y-axis. Means these two are parallel. That's why both will have same unity vector. Along a positive y-axis, you have unity vector j cap. So AC vector is written as B. B is the length, and the unity vector will be j cap. And your magnetic field is this much. No. Just like in a previous case, we'll find cross product of this term, and then this magnetic field, one by one for each term, and we get this result. We found this one. In the similar manner, we can find the magnetic force on CD arm, this one. See, this CD vector, this CD vector is anti-parallel to your positive x-axis. Means if you have a unity vector I cap along positive x-axis, then you will have a unity vector along CD minus I cap. No? Why? Because it is anti-parallel to your positive x-axis. And along positive x-axis, you have unity vector I cap. That's why along CD vector, you will have unity vector minus I cap. Minus I cap. So this force is CD vector cross B, and CD, the magnitude of this length is, this is in a rectangle. It is in 3D. That's why it looks like, the shape looks a bit different, but it is a 3D diagram, and this loop is the rectangle. So opposite sides are equal. If this side is A, this side is also A. So the magnitude of CD vector is A, and unity vector along in a CD vector is minus I cap. That's why here you have minus AI, and this is your magnetic field. And again, you will find the cross product. Here we can keep the bracket. Okay, you can find the cross product of this term with all of these terms separately, and you will get this one, just like previous cases. And similarly, we can find the magnetic force experienced by the arm, current carrying arm dy. Its arm is a wire here, current carrying wire. So the force, or the magnetic force experienced by the DO arm is current and length vector of DO arm, DO vector cross in a B. And see, DO vector, the direction of DO vector, DO vector is the direction of DO vector is opposite to the direction of positive y-axis. So if you have a unit vector j cap in this direction, we'll have a unit vector minus j cap in opposite direction. So you can write in a DO vector as, we can write in a DO vector as, magnitude of length of DO vector, that is B, and we have unity vector in this direction minus j cap. And this is your magnetic field. Now you will just take cross product of these two vectors, and we get this much. Is it clear up to now? Calculation of magnetic force on its arm. Is it clear? If you have doubts, okay. This is the simplest way to find out the torque in a current carrying loop, in a uniform magnetic field. And just analyze one thing here. See here, the force on OA arm. The force on OA arm, its value is this much, OA arm. And the force on CD arm, OA arm, you have force in this much, IA, in bracket you have BY cap minus in a BZ and a J cap. And see, the magnetic force experienced by the CD arm is how much? This much. Now, just analyze these two values, we have everything in the same IA, same thing, and C this in a vector quantity. This is just this one is just a negative of this one. If you multiply by a negative here, you will get this result. So what is the meaning of this? FCT factor is just a negative of OA factor. This means what? The magnetic force on CD arm has same magnitude as the magnetic force on OA arm, but the direction is opposite. In the similar way, you just look at magnetic force experienced by AC arm and the magnetic force experienced by the DO arm. See the value here. You have this much. If you multiply this quantity by minus, you will get this one. Minus into minus, you will have plus here. Plus into minus, you will have minus here. This means the magnetic force experienced by DO arm is just opposite, has the same magnitude but opposite direction to that experienced by AC arm. No, so you can also write like this. Your FDO is just negative of is negative of FAC. The magnetic force on this arm is just opposite of the magnetic force in this one. And so both have same values, but the directions are opposite. And FO, FOA, and the FCD means FCD is FOA. This thing should be clear. So we are seeing here, the force on this arm is just has the same value but opposite direction to that experienced by a OA arm, and the force on this arm, DO arm, has the same value but opposite direction to that of that of the force on AC arm. So yesterday, we had calculated the net force is 0. Now we have force on its arm, and we know the net force. We know the net force on the loop is 0, and we already calculated yesterday. And you can also conclude by observing the general relations. So now let's move to another slide, and we'll be calculating torque now. Just a minute. To work. Okay. Just a minute. Let me. It was working. I reject. We need to move to next slide. Okay, just wait. We calculate. We finish this one. No. Just a minute. Wait, it's not happening. Okay. Again, same thing. Yeah. So we have to stop annotate, and then we have to move to next slide. Okay. Now, let's discuss one thing. When we calculate a magnetic force on any state in a current carrying conductor, suppose if you say the magnetic force on this arm is in FM, this means what? This means you have so many free electrons moving in the conductor. So by saying that the magnetic force experienced by this conductor is FM, this means the average force, this implies the average force acting at the midpoint, of the conductor. That is the meaning of the magnetic force experienced by a conductor. You have one charge, then it is fine, you write magnetic force as you say charge magnetic force experienced by this moving charge of particle is q v cross b. But in the conductor, you have so many free electrons moving. So by saying that you have the conductor is experiencing magnetic force Fm, it means that this is the average force acting at the midpoint of the conductor. So we are taking the midpoint of each arms. The midpoint of OA is E, the midpoint of AC is F, the midpoint of CD is Z, and the midpoint of this DOR is H. So by saying this force, where does this force act? This force acts at the midpoint of the arm OA. Similarly, the force in AC, the force AC acts at the midpoint, that is at the point F of the arm in AC. That is the meaning. And since the net force, on the current carrying in a loop is zero, we already found a story, right? Since the net force experienced by your inner loop is zero, this means the forces are in equilibrium. Force on this arm is cancelled by this. The force on this will be cancelled by this. This means you can say either the forces are in equilibrium, or you can say the net force on the loop is zero. Then in rotational dynamics, we know that when the net force is zero, then net torque about any point should remain same. You might have studied in rotational dynamics that if net force is zero, or you can say the forces are in equilibrium, then the resultant torque about any point, the resultant torque due to all these forces at any point should be the same. And in this situation, we are calculating the torque about the point O. Means we are calculating the torque due to all these forces about the point O. So how to calculate the torque? We know torque, you might have studied this one, R cross F. We have found out force, and we have to find the perpendicular distance between this point, the point about which we want to calculate torque, and the point of application of the force. Means when we calculate torque due to this FOA force, we will take R vector as OA vector, and F force as F OA force. No, R vector as not OA, it will be OE, because your force, the force on this arm is acting at E point. This is the point of application of force, and we want to calculate a torque about point O. So your R vector will be OE, and how much will be OE? Since E is the midpoint of your side OA side length is A, so OE will be how much? A by 2, and the direction is along a positive x-axis. The direction is along positive x-axis, and along a positive axis you have unity factor I cap. That's why A by 2I. Similarly, the force on the magnetic force FAC will act at the midpoint in the AF. So when you write the torque due to this force, then what will you do? You will write in R cross F, and R will be the distance between this point O and the point of the application of the force, that is F. And how much will be OF? How much will be OF? OF vector. You can write in component form. You can write in a component form, and you might have studied factors. If you have a vector here, and in order to write in component form, what we do, from the arrow we draw perpendiculars on both axes, and then this is your x component and this is your y component. Similarly, you can do here, this is your vector, OF is your vector, OF is your vector. Then we are in a drawing from F point, we are drawing perpendicular on x-axis and on y-axis. Then see, this is the OA is the x-intercept, so it will represent x component of OA vector. So you can write OA vector as x component is AI, length of OA is A, and unity vector I. And how much will be? Again, we are for y component, we are drawing in a normal to the y-axis. So OH represents OH represents a y component of OF vector, and OH is nothing but B by 2, and unity factor along y-axis is J. So this is how we can express OF vector. Similarly, for the R minus CD, we have to find the this OG vector, because your force is acting at a G point. The force in FCD is acting at midpoint of CD, and we have to take R vector as OG vector here. In this case, R vector will be OG, means position vector of G from the point O, OG vector. And how can you express OG vector? See here, this is your OG vector, and for writing its component, what we do, we draw perpendicular from G point to x-axis and perpendicular to y-axis. So OE will represent x component of OG vector, and see, if you draw a perpendicular from G to y-axis, then OD will represent y component. No? So OE is the x component, and how much is this one? A by 2, unity factor is I, and OD will represent the y component of OG, and that is your BJ. In the similar way, midpoint of DO arm is yes. So OS vector will be how much? OS vector. This is the point of application of force, and this is the point about which we want to calculate the torque. So your R vector in this case is OS vector. And how much is this? This side length is B, OD is B, so OS will be B by 2, and you have unity factor along positive y-axis as J. Are these things clear? We are just using the concept of vectors. Okay. So these things should be clear now. Now let's try whether we are going to move next slide or yeah. Now we have to calculate the torque. This time it worked directly. We have to calculate the torque due to all these forces, FOA force acting at the, FAC force acting at the F, and this FCD force acting at the, and FDO force acting at the S, about the point O. We have to find torque due to all these forces about the point O. And I said earlier, as the net force on the loop is zero, that is, as the forces are in equilibrium, the net torque about any point due to all these forces should be, should be the same. So, in order to find the net torque, what do? We find it a torque due to each force, and we take the vector sum. Vector sum of all these torques will be the net torque. So, in the first case, let's find the torque due to FOA force. The force on this arm. So your R vector in this case is this, the vector joining O point and the point of application of the force E. So we write OE, and the force at E is FOA. We have given the name FOA for the force acting on OA arm, and this force is acting at the midpoint. So this is your first torque, and the torque due to the force acting on the AC arm is your R vector, R vector, the vector joining the point about which we want to calculate torque, and to the point of application of force. The force on this arm is acting at F. So your OF vector is the R vector, and the force acting at F is FAC. Similarly, the torque due to the force acting at G or on CD arm. The force on CD is acting at its midpoint in G. So your R vector will be OG vector, cross the force acting. We are using this formula. So similarly, the torque due to the force acting on DO arm, the force acting on DO arm is acting at the S point. So your R vector will be OS, and the force is FDO. So this thing. And in the previous slide, in the very first slide, we calculated the force. We calculated the force FOA, FAC, FCD, FDO, and we also calculated the value of OE, OF, OZ, and OAS. So we have to just put the values. We put the value of OE vector. OE vector. This length is A/2, and direction is I cap. And your FOA force was this one. And in the very first slide, we calculated the force FOA. So we have to take the cross product of this. Similarly, we put the values of OA vector and FAC vector. Here, we put the values of OA vector, and this OA vector, this OA vector as the X component, as OA, and a Y component OS. OA is in AI, and OS vector is B/2Z. In a similar way, we have the values of all these, OG, OG vector we have calculated. Its X component will be OE, that is A/2I, and Y component will be, we draw perpendicular to Y axis, and your Y intercept here is OD. So it is how much BJ. Like this, we can write the values of all OS. See how much is OS? B/2, and the unit vector along in a positive way. Y-axis is Z, so you'll B by 2 Z, and the force on this arm, the arm is this one, we calculated this in the first slide, the values of all the forces. So you have the expression of torque like this in a cross product, R cross F, R cross F, R cross F, R cross F. So what will you do? You will just multiply A by 2 with IA and remove this outside, and you take a cross product of I vector and these vectors. Similarly, you can take cross product of these two vectors. First you take cross product of AI vector with each of these terms both separately. Then what you do, you again take cross product of B by 2Z with each of these two terms. Same thing for these all. And if you simplify, you will get the final result. Let's see. So you find the values of its cross products, simplify, and how much will be left? Let's see. Okay. So after simplifying, we'll get this much. This much will be the left. I, AB, A is this side length, B is this side length. In a rectangle, one side is A, another side is B, in this case. So you can take IAB common, and in a bracket you will be left with, you can take IAB, IAB, you can remove outside, and in a bracket you will be left with BXJ minus BY, I. And this can be, expressed as, this can be expressed as cross product of, these two vectors. If you take the cross product of these two vectors, then see IAB, fine, IAB, you can write in a outside, and see cross product of a K vector with I vector, K cross I, K cross I is how much, K cross I is J, this is how you calculate I cross J, J cross K, K cross I. See, K cross I is J. So what we will have, BX, and then you will have J. If you take in a cross product of these two, then again, if you take in a cross product of this in a K and this term, K cross J, see, K cross J, you go anti-clockwise. Means if we go anti-clockwise, then we have to take a minus, J cross K is I, J cross K is I, but if you take cross product of K cross J, then you will have minus I. So you have BY and I. And if you take in the cross product of this BJK with this K, K cross K is 0 because the angle between them is 0 degree. And when the angle between two vectors is 0 degree, the cross product is 0.